Survival analysis. Frequently the case that we are studying populations and we want to estimate how long time the population stays alive. Just as in other occasions, we often do so through a sample. A typical way to represent this data is just to look on how long time after we first encounter the patients do they sort of disease. And this will give us possibilities now to model the survival time of a certain condition. So say that we have an onset of cancer and we want to see how many years the patients stay alive after the first onset of the disease. That's a typical scenario where we use survival analysis. A very efficient way to study such things as using a survival function, often abbreviated S of t, and that's the probability of staying alive after a certain moment in time. So you can sort of estimate the for instance the survival rate after 8 years, and so you can tell what fraction of the patient are still alive after 8 years. This can be used to compare different treatments. So say that we have two different populations, one is given treatment A and another one in treatment B. Which one is the most efficient? Well, the one way to tell it is just to see what fraction of patients are alive at a certain time. You can also think about scenarios where we want to make regressions out of this type of data. So say that we have a certain fraction of patients alive at a certain point in time, or we want to observe all the different patients and see how long time they survive, given how large the tumor was when they first were diagnosed. This could lead us to an interesting regression model. So we might make a linear regression between the time alive and the tumor size. This is a completely fictive case, by the way. Unfortunately, this is not as easy to do in regular data as you might think. And the reason is that we often don't observe data this way that I've demonstrated it first. This type of data is called uncensored data. That should be said in contrast with censored data. Because what regularly happens in a study, and this is a fortunate fact for the patients in the cohort, but maybe not as fortunate fact for us as want to make a regression out of the data, and that's that a sizable fraction of the patients in the study are actually surviving at the end of the study. So we can imagine that we have patients that are surviving to a much longer time in the future. But at some point, we just have to close the investigation and say that, well, actually, we do just treat the patients that are still alive at the end of the study as survivors, and we now try to compensate for that fact in our when we do our analysis later on. And as a matter of to grave this problem is actually that not all patients are entering into the study at the same time. Normally, we actually start the study at a point, and then we collect the patients as they enter into the clinic. This leaves as well as to very different span of time that they can be affected. So from the data to the left here, which is sort of the actual observation of the death times of different patients, we can now we instead normally see something looking more like the distribution here to the right, where we see the onset of the disease and the outcome of the patients, and the blue lines here represent patients that are alive at the end, and the red lines is the patients that are not surviving. Although it might be desirable to observe the distribution of survival times for our sample, it's just that we don't have this full distribution. So the red distribution here to the left is the only part we work really can depend on. The rest of the patient will still be alive, so we don't know what shape they take. This poses a problem for the further analysis. So we need a way to sort of compensate for the fact that the patients are still alive at the end of the study. So the Kaplan-Meier estimate is just estimate of the survival time, and it's formed as a piecewise product. So at each point of time, you just take the number of events, that is the number of individuals that died during this time, the piecewise time, and you divide that by the number of individuals. So in this particular case, the first event that happens in the flow is actually somebody deceasing during the study time, and that's then you take that times or divide that by 25, which is the number of patients alive. So that will form you then give you an estimate of the survival function as 1 minus 25 at 24 divided by 25 at that point of time. And for the next event, these are all survival events, those blue lines here. But then at when you reach the fifth event here is actually a disease event again, and at that point you take the number of survivors, that is 21, and you put this into the equation. So it's now what you had before times 1 minus 1 divided by 21, which is a new survival function. So this way you can sort of multiply yourself into the best estimate of the survival function. Okay, so you can now readily make these kind of estimates and plot the estimated survival function as a Kaplan-Meier estimate. This allows us now to estimate the fraction of patients alive at a certain point in time. And this is compensating for the fact that some of the patients are surviving. And you should say that in contrast, that stands in contrast now to a naive classifier, where you would just look on how many of the patients are actually alive among the ones that died during the study. How many are there alive at a certain point of time? This would not give you the same type of function, and it would not be a very accurate estimate of the survival time. And the real benefit here is that we can start to compare different Kaplan-Meier estimates. So if we have two different treatments, we can sort of make a differentiation between the treatments by estimating or to look at the Kaplan-Meier estimates of their survival time in the different samples. And this case, and we will then sort of favor the treatment that gives you the highest survival function. Sometimes we want to make more advanced models, like regression models. The probably most popular and well-known one is the Cox proportional hazards model. This allows you to study survival as a function of different variables. It takes the sort of the setting where this is an additive model, so you could just sort of throw in as many of different factors that you feel comfortable testing. So takes its onset that you have a baseline survival rate, lambda 0 of the time. Actually, you don't have to estimate this survival function, but you rather take interest in what's coming after that, the exponentials of the factors x, y that you are modeling. And there's a way now to fit the regression through those using a regression model, which gives you a couple of coefficients beta here. And this allows us now to estimate the hazard over time. So what you learned here is to observe what we call sensor data. And survival analysis is exactly done for that, to observe sensor data. That is studying samples where we actually don't see the end event of all the data. We see that it's censored because it's sort of we're not given disclose the full information. So this is a way to operate with when we don't have the end events of things. Of course, here I've been very macabre and been talking about survival and death as a physical thing. Often this can of course be used for other processes as well. And it's actually a very popular model, not just for patient survival. There are plenty of examples of in the literature.